Okay, we have Chapter P, Section 3, the second part of it. Rationalizing the denominator when the denominator contains two terms. You're going to simply multiply the denominator by what's already there, but you just change the sign in the middle. This is called multiplying by the conjugate. And when you rationalize the denominator of examples like these below, you're going to multiply by the conjugate of the denominator over itself. That will be your clever form of 1. So if the denominator contains 7 plus the square root of 5, you're going to multiply by 7, subtract the square root of 5. These two things are called conjugates of one another. The first term and the last term are exactly the same, but the signs in the middle are different. So I would take this quantity and this quantity and multiply them. And when I do that, this is what your output's going to be. So I'm going to write things as such, meaning 7 times 7, I'm going to just rewrite it as 7 squared, just to get used to seeing things like this in terms of squaring, because when we do complete the square, you'll be having to do that anyway. So here I've got 7 times 7 is 7 squared. 7 times the opposite of the square root of 5 is the opposite of 7 times the square root of 5. And then here, when I multiply these two, I've got positive 7 square roots of 5. And then when I multiply these two outside guys, I get, it's negative, positive times negative is negative, and I've got root 5 squared on the outside. And so what happens here is these terms in the middle, well, they are opposites of one another, and that's what multiplying by the conjugate does. It eliminates those inside terms. And then what you see is we have 7 squared is 49, the sign is negative, and then the square root of 5 squared is 5, and 49 subtract 5 is 44. And this technique will eliminate the denominator of any radicals. If you don't multiply by the conjugate, you're still going to have a radical in the denominator, and your job is to get the radical out of the denominator. Okay, same thing here. If you notice, I've got root 5 minus 3, root 5 plus 3. They are conjugates of one another, and when I multiply these together, I get root 5 squared. And then I've got plus 3 root 5, subtract 3 root 5, and then positive times negative is negative, and this gives me 3 squared. Okay, of course, the conjugates provide that pair of opposites. They go away, and I end up with root 5 squared is 5, subtract 3 squared is 9, and I end up with negative 4 in this case. And the last one, notice they are conjugates. First terms are root 3, second terms are root 2, one's plus, one's minus. You know, once you get used to the conjugates and knowing that the middle terms are always going to sum to 0, then you don't even have to write them. You know, this thing would just be root 3 squared. You know, double check it. So this is going to be, you know, subtract root 6. Add root 6. Now remember, I'm using that product rule, right? If I have root 3 times root 2, that's the same as root 3 times 2, and 3 times 2 is 6. That's how I'm getting these. And then, of course, sign's negative here, and that's root 2 squared. And as you see, the middles are going to sum to 0. Root 3 squared is 3. Root 2 squared is 2. And 3 subtract 2 is 1. Okay, so that'll come with a little bit of practice, unless, you know, it's coming back to you and you're like, oh, yeah. You'll have some stuff like that to do in your radicals packet as well. So now on to doing the actual types of problems that you will see in the radicals packet. I look at this and I'm like, oh, okay, 3 divided by 3 plus root 7. I do have a radical in the denominator. It's an irrational number, so I have to rationalize that denominator. When you have a quantity like 3 plus root 7 in a denominator that includes a radical, you have to multiply by the conjugate over itself. That's the only way the radical can be removed. Again, I like to write the original problem down. And then I ask myself, what's the conjugate of 3 plus root 7? And I answer myself and say, well, it's 3 subtract root 7. And then remember, this fraction has to be a 1, because I don't want to change the value of it, I just want to change the way it looks. So this is really 3 subtract root 7 over itself. Now, these are quantities. And so in the denominator, you have to FOIL. In the numerator, I wouldn't distribute at this point. I would simply write it as 3 times the quantity, 3 subtract root 7. Because remember, you're going to end up with some integer here in the denominator. And you want to see if that's going to be reducible with this integer that's outside. Of course, 3 times 3 is 3 squared or 9. Remember, the middles go away. This is minus 3 root 7 plus 3 root 7. I don't have to write it. And then this is subtract root 7 squared is 7. And so my final answer here then is 3 times the quantity, 3 subtract root 7, all over 9 minus 7 is 2. And since the 3 and the 2 have no common factors, I'm done. You could write it out as 9 minus 3 root 7 over 2. That would be fine, but I just leave it like that. That answer is acceptable. Example B. I've got 5 over the square root of 3 subtract 1. I've got a root 3 here, and I have to get rid of that radical in the denominator. So I have to multiply by the conjugate of the denominator, which is square root of 3 plus 1 over itself. And when I do that, I end up with 5 times the square root of 3 plus 1 over root 3 times root 3 is root 3 squared, or 3. The middles are going to sum to 0, and then I get this minus 1. And so my final answer is 5 times quantity, root 3 plus 1, all over 2. Why don't you try the last one? Pause the video, and then turn it back on to see if you're correct. Okay. Hopefully you paused the video and you tried this problem on your own. Root 7 subtract root 3. I have to multiply by a clever form of 1. That would be the conjugate of the denominator, root 7 plus root 3, over itself. And I get 11 times the quantity, root 7 plus root 3, all over root 7 times root 7 is root 7 squared, or 7. Middles are going to go away. That's going to be subtract root 21, add root 21. And then here root 3 times root 3 is root 3 squared, or 3. And 7 subtract 3 is 4. 11 and 4 have no common factors, so I can leave it like that. Okay, if you have questions on those while you're working on the radical packet, just send me a message. Of course, I can't help you on the radicals packet itself, but we could take a look at problems that are similar to it. Okay, on a side note, this will help you with the radical packet. So I'm just going to cover this up and write an example problem right here. So let's say I have the square root of r to the power of 7 times s to the power of 10 divided by the square root of r squared s to the power of 15. Now we can use the quotient rule, and let me move this. And we can use the quotient rule here. 2 of these will divide out 2 of those. So I can simplify this. This could become r to the power of 7 minus 2 is 5. And then here, notice there's more in the denominator than there are in the numerator. So that would be the square root of s to the power of 5. Now, I've got to rationalize this denominator, which means I need to make this be some square. S to the power of 5 is not a square. But any exponent that's even is a square. Excuse me. And so I can say this is equal to the square root of r to the power of 5, power's on the inside, and the square root of s to the power of 5. And remember, my goal is to get the denominator to be a perfect square. Well, if I multiply by root s over itself, that gives me in the numerator the square root of r to the power of 5 times s. And in the denominator, this makes this the square root of s to the power of 6. I'm going to want to simplify this in the numerator, so I'm going to rewrite this as r to the power of 4 times r times s. And down yonder, I'm just going to keep it as the square root of s to the power of 6. Okay, this is going to come out as r squared. This rs has to stay in, so r squared comes out times the square root of r times s. And this, s to the power of 6, if you take the square root of it, well, I don't know if you remember from Algebra 2, but with rational exponents, it's power divided by root. So the power is 6, the root is 2, so this would come out as s to the power of 3. And technically, because this was an even power on the inside, if s were to be negative, okay, raising it to the power of 6 would keep it positive here, and that would be a real number. But if s were negative, taking it to the power of 3 would be a negative number, and it wouldn't be equal. So technically, you should have absolute value bars around that. I'm not going to be a stickler for this, especially on the radicals packet, because on the radicals packet it says assume all variables are positive. Okay, so again, you can rewind the video and watch this part again. This should help you on that radicals packet. Sorry about that. Okay, back to the notes. Other kinds of roots. We define the principal nth root of a real number a, symbolized by the nth root of a, as follows. The nth root of a equals b means that b raised to the power of n equals a. It was just kind of like that thing with square root of 81 equals 9. Why? Because 9 to that root, which for square root it was 2, 9 squared equaled 81. It's the same thing. If n, the index, is even, then a is non-negative. It means it has to be greater than or equal to 0. Equal to 0 because 0 is not negative. And b also has to be non-negative. Got to be bigger than or equal to 0. But if n is odd, a and b can be any real number. And this just simply means I can't take an even root of a negative number, but I can take an odd root of a positive or a negative. That's all that means. So, for example, I'm going to simplify the cube root of 125 and say that it equals 5. Why? Because 5 to the power of 3 equals 125. And the fifth root of negative 243 equals negative 3. Why? Because negative 3 raised to the power of 5 is exactly equal to negative 243. Okay, I'm going to stop the video here and pick up with another video, only because I am recording during K-Block right now, and they're going to come on the speaker with announcements, and it's going to interrupt my video.